successful businessman. And along the years, there were many, many distinguished speakers that gave these lectures. 9 of them received the Fields Medal a few years after the lectures. And so I'm delighted to have today's lectures, and they will be introduced by William. I pass mic to him.
Merci, Octave. Tout le monde m'entend bien? Mon nom est William Bichak-Krempa. Je suis professeur de physique au département de l'Université de Montréal, ici. Mon plaisir d'introduire mes collègues Duncan Haldane, le conférencier aujourd'hui. Puis Duncan, en fait, parle français. Il parle plusieurs langues, donc anglais, français, allemand, un peu de slovène, je pense, et peut-être d'autres langues que j'oublie, à part les mathématiques, évidemment. Donc, faites attention à ce que vous dites. I'll switch to English just so that everyone follows, because we have people for the conference that don't speak French. So Duncan was born in London, Great Britain, received his PhD from Cambridge University in 1978. His advisor was the future Nobel laureate Phil Anderson, who then eventually moved back to the States. He was in Cambridge at that time. Haldane, after his PhD work, he moved to Grenoble at l'Institut Laue-Langevin, where he learned even more French. And then he came back to the US, where he was at the University of Southern California, Los Angeles, then the famous Bell Labs in New Jersey, where many physicists in those days did great discoveries. Then moved back to California and San Diego. And since 1990, he's a professor at Princeton University, where he holds the Sherman Fairchild University Professorship. So that's a distinguished professorship. Obviously, he received many prizes. One of them you already know about. So I'll just list a few, because otherwise we'd be here for an hour. He's a fellow of the American Academy of Arts and Sciences, a fellow of the Royal Society of London, the ICTP Dirac Medalist in 2012, if I remember, and finally Nobel Laureate of Physics in 2016. He shared the Nobel Prize with 2 other British physicists, so David Tallis and Michael Kosterlitz, for, and I quote, theoretical discoveries of topological phase transitions and topological phases of matter. Okay, so I'll say a bit more about that. But first, it's interesting to note that Haldane did not disappoint his academic ancestors, because Phil Anderson had a Nobel Prize, and he shared this prize with his advisor, Van Vleck. And so Van Vleck's advisor was Campbell, who did not win the Nobel Prize, but his advisor, Bridgman, won it in 1946. So only one person in his lineage skipped it. And I was asking him if any of his students would win the Nobel Prize, and he has someone in mind, which I agree eventually could win the prize. So let's keep an eye on that, which would be the longest Nobel lineage, I think, in all the disciplines. So physics. So in his research, Haldane did many, many things, but I'll focus on the research that was récompensé, was rewarded by the Nobel Prize. So this was for his work where he was using topology, a branch of mathematics, to understand interesting states of quantum matter. And you can divide these systems in 2 categories. The first one being 1D chains of atoms that are magnetic. We call them spin chains. And Haldane discovered, using topological methods in quantum field theory, that depending on whether the atoms have odd or half, not odd, but half integer or integer spin, has very big consequences on the behavior of these spins and excitations in these spin chains. That's the first part. And the second class of systems is a quantum Hall effect, which happens when you take electrons in a plane and apply a very strong field transverse to that plane. You get topologically robust states of matter, which are actually used for metrology today. That's how the kilogram is defined. And Haldane did many things in that area, but one very striking discovery is that he showed that you, in fact, don't need the very strong magnetic field. Some models have that effect without any applied field. And his model was later used as one of the seeds for this booming field of topological insulators, which is perhaps one of the most active fields in condensed matter today. So I think this paper that Duncan wrote in the 80s had very few citations at the beginning and eventually just exponentially exploded. And today is one of the seminal papers in topological states of matter. And so both of these systems have a deep connection to a class of quantum systems that are scale invariant that we call conformal field theories. And these are at the center of the workshop that Duncan is attending this week and is going on for 3 weeks. He's actually giving 2 more lectures, Wednesday and Friday, that are more specialized, but you're all invited to those as well. And maybe I'll end on a small note that's a bit more personal. So I think many of us, of his colleagues, know Haldane for his very big originality and the depth and breadth of his discoveries, but we all know him also for his generosity in discussing physics. There are many anecdotes. I have my own. When I was a postdoc at Perimeter Institute, I had a flight to catch and Duncan was visiting and I absolutely wanted to talk with him before I left. So I booked a meeting with him and I almost missed my flight because when Duncan starts talking about physics, it's like tap is open and it's very hard to stop. And I was listening, captivated. And I think many of us have similar anecdotes. I think that someone that busy is so generous with his time. And today, we'll see more of that. So without further ado, thank you, Duncan, and the floor is yours.
Thank you for inviting me. Today I'd like to topological quantum matter entanglement in the second quantum revolution. And I'll try and I've got some quite basic stuff in here, so I hope the experts won't mind. Okay, so as we understand quantum mechanics, the key message I'm going to give from this talk is that we're now in a phase where we're getting to understand quantum mechanics better, and all kinds of new and strange possibilities for the materials of the future and the technologies that they might allow are emerging. And this is actually, this new understanding has been emerging in a series of unexpected surprises, really, that have led us to new ways of thinking about quantum materials. And yeah, things have completely changed since I was a graduate student at mechanics. So it's just the heart of the talk. So the modern laws of quantum mechanics were established in this period about 90 years ago, 1925 to 32, and here are the laws of quantum mechanics have not changed. They stood the test of time and remain unchanged, and all the tests that have been carried out to date have confirmed that quantum mechanics laws as formulated are correct. But that doesn't mean to say we know, we really understand quantum mechanics. And in particular, just because we know the laws of quantum mechanics, it doesn't mean we immediately know all the things that they permit to occur. And the anecdote on this is so my original thing was Maxwell completed the laws of electromagnetism in 1864. And it's taken a long time to bring everything to fruition from electromagnetism. It's still an active research subject, and new things going on, like photonic crystals, and then this led to all this technology. And as you can see, I had it wrong about who the conversation with Gladstone was, but Faraday, who did the third law of electromagnetism, was apparently asked by the British Prime Minister at the time, Gladstone, who said, this is all very interesting, Professor Faraday, but what's it good for? And Faraday apparently replied that he couldn't say what it was good for, but he did know that one day Mr. Gladstone would be passive. I think he wasn't yet the Prime Minister, he was the Minister, the Chancellor of the Exchequer at the time. So we don't know, quantum mechanics hasn't been used yet, but now in the form that people are trying to use it for. But there's a lot of hope now for the development of new technologies and new computation devices and things. So starting around 1980, new insights into quantum mechanics started to emerge. And in our field, in condensed matter, new unexpected quantum states of matter, which we now call topological states, started to be discovered. And in a parallel development, starting earlier in the 50s, Richard Feynman started thinking about what would happen when you got down to the atomic scale of making computers. He was interested in, how would you make a computer to simulate quantum mechanical processes? And he concluded that you needed a quantum computer to do it. So he began thinking about what would happen on the very small scale, and there's a famous essay he wrote, which was called "There's Plenty of Room at the Bottom." I think at that time in the 60s, there was a kind of angry young man play called "Room at the Top," social play, and the room at the bottom with the essay. And what's been happening in recent years is that we're now really trying to get a very fine, exquisite something with a hammer and see what flies out. Now we're kind of trying to manipulate quantum systems, directing them. And this control of quantum states is really the central aim of a lot of the new things which are going on. And it's on the way to being achieved. And surprisingly, more progress than one might have believed at the beginning seems to be being made. So this has led to this idea that after this period in the 20s, we're now in the second stage, the second quantum revolution, where we're really coming to terms with quantum mechanics on a much more intimate level. And the hope is that within the foreseeable future, the next 10 to 20 years, a lot of developments. So quantum mechanics on the basic level, this is a public talk apparently. So the original idea of the atom was by Niels Bohr, who had a kind of model for the atom a bit like a little solar system, except quantum mechanics kind of made a finite set of allowed radiuses of the orbits for the electrons to go around the nucleus, like the Earth around the sun. So Bohr discovered that not all these orbits were allowed by quantum mechanics, and he called the allowed ones orbitals, which is a name that has stuck. And Schrödinger's picture developed in around 1926, the kind of modern picture. And Bohr's little clean orbits become essentially a box in which you put the atom, put the electron. So we don't know exactly where the electron is, we just know it's somewhere inside the box. And the box is approximately a kind of region enclosed by what Bohr called the orbit. So Heisenberg uncertainty principle let's see if I can get rid of this thing here at the bottom. Just a minute. Yeah. Heisenberg's uncertainty principle turns Bohr's kind of orbits into a kind of fuzzy cloud around the nucleus. And but we still call this box, which after Bohr. Oops. Stop working. Oh, move the thing out of the way. Okay, now it's going. Okay. So here actually, so we can imagine the box as either empty or full. It's like a two-state system called empty 0 and full 1. And so actually, this is a picture of the electron cloud. You know, it's a real picture of an atom. It's not a hydrogen atom in its lowest state. It's a hydrogen atom in a very excited state. You know, the orbit is called the Rydberg state. It's going around at a much larger distance than the ground state orbit. But you can see it. You can actually image this fuzzy cloud of the electron in its uncertain position inside the box. So the Pauli exclusion principle is going to be important. So the Pauli exclusion principle says that two electrons can't be in the same state, or roughly speaking, they can't be in the same place. So many kind of popular talks on quantum mechanics emphasize the Heisenberg uncertainty principle, but actually the Pauli exclusion principle is perhaps the most fundamental of these fundamental laws of quantum mechanics, because you know, in everyday life, the reason we don't fall to the center of the Earth when gravity pulls us down is because the Pauli uncertainty principle prevents our shoes from, the electrons in our shoes from occupying the same space as the electrons in the floor. Newton thought it was obvious that there's something called a reaction force. It's an empirical observation. You press on something, it presses back on you. But, you know, he didn't feel that the explanation is obvious, but actually it's quantum mechanics because the atom itself is 99% empty space, so it's actually the Pauli uncertainty principle that prevents penetrating the region owned by other matter. So, okay, so the Pauli exclusion principle says that two electrons can't be in the same state. But what defines the state of the electron? So actually, in addition to its position, there's another degree of freedom in the electron called its spin. It's like a little rotating top, a spinning top. And this spin points along the direction of the axis of the top. So actually, we can put two electrons in the same box, provided that they're occupying the same region of space, provided that their spins are pointing in opposite directions. And we can't actually tell which direction the spins are pointing in. It's only important that they're pointing in opposite directions. So two electrons, one spin pointing up and the other one down here is exactly the same. Pauli exclusion principle says that something called the wave function or the Schrödinger state of the electron pair has a property that if I interchange two electrons, it's represented by a general complex number. That number has to go to minus itself, which is the essential Pauli feature of these particles called fermions, which what electrons are. Apparently, Pauli was actually quite disappointed to discover that electrons were fermions. He would have much preferred them to be bosons, which letter to somebody, but unfortunately, he found electrons to be Fermi-Dirac statistics, not Bose-Einstein statistics. But anyway, this pair of electrons up, down, minus down, up, which tells you they actually don't know which electron is up and which is down. In the kind of mixed state where both up and both down, all the time opposite to each other. This is actually the maximally entangled state of two electrons. So this plays a key role in thinking about entanglement. And of course, you probably remember high school chemistry, which was actually phrased in terms of putting electrons into little boxes, and you can put two electrons, one spin up and one spin down in each box, and you build up the periodic table, and you understand all the properties of different atoms in a very simple. Actually, for many purposes, about the maximum quantum mechanics you need to know, or some interesting quantum mechanical aspects of certain interactions, certain chemical interactions. Okay. So the chemical bond that binds atoms into interesting clusters, like us, for example, basically everything is really held together by an entangled pair of electrons, because you put a pair of electrons in between two atoms, put them in the same place in between the two atoms, you have to have one up and down spins. And this, of course, holds everything together, makes matter interesting as opposed to just a load of atoms floating around. And so this, the chemical bond is perhaps the poster child of entanglement. Okay. Actually, entanglement now seems to be the central property of quantum mechanics. In the past, it used to be the Heisenberg uncertainty principle. And when I learned quantum mechanics, I don't even think we mentioned entanglement, right? Entanglement, especially as Einstein had proposed it, was a kind of problem that philosophers of physics worried about, and real physicists just played with their boxes. Right? But now it's really turned into, it's been recognized really as probably the central property of quantum mechanics, and it was first pointed out by Einstein. And it's also, nowadays, it's become viewed as the fuel which is going to drive this possible technological revolution of quantum information processors. Einstein, of course, got his Nobel Prize, not for relativity or gravity or anything. He got it for his work on the photoelectric effect, one of the early, after Planck, one of the second really observation important in early quantum mechanics. But by 1935, Einstein became convinced that quantum theory had to be wrong, right? He rejected the quantum theory. He said it's got aspects which don't make sense with local reality, as he called it, or local realism. And he identified this property of quantum mechanics, which he felt was so crazy it had to be wrong. And he called it spooky action at a distance, because to make fun of it. But Schrödinger was more, pragmatic, and Schrödinger came up, I guess, in German with the word Verschränkung. In English, it's become entanglement. In French, it's called Entanglement. I think every language seems to have adopted a different word for this new entanglement. But Einstein felt that he then went on to think up a thought experiment that he felt, when it was done, was disposed of quantum mechanics into the dustbin of history. And so Einstein was worried about what happens if you take this chemical bond where you have the spins up and spin down, and manage to stretch it, keeping the spins in this up, down, down, up state to large distances. And he said, could it really be up, down, or down, up, and it didn't matter until you measured it? And, you could make one electron here and one electron in Alpha Centauri, for example, right? And and so he worried about, if you measure the electron as pointing up in this way, does that immediately make the electron point down on the other side of this long entangled string? He felt that's some kind of violation of relativity, that you could communicate things instantaneously, faster than the speed of light. And of course, actually, it doesn't mean, it actually doesn't imply any violation of relativity. You can easily make things move faster than the speed of light, apparently. I can take the pointer and shine it not on the ceiling, but on the moon. And I can make that dot on the surface of the moon cross the surface of the moon much faster than the speed of light. But no one on the moon can use that to communicate any information from one point on the moon to the other point on the moon faster than the speed of light. So anyway, it doesn't violate anything. And Einstein and Podolsky and Rosen proposed this thought experiment. And actually, Podolsky went to the New York Times and told them Einstein has come up with a way to get rid of quantum mechanics. And that made the headlines. I guess no country had been invaded that day or whatever. It must have been a quiet day for news, but anyway, New York Times made this the headline of the day. And Einstein was apparently so furious with Podolsky that he never spoke to him again. He went on to collaborate with Rosen on something that the string theorists or the black hole theorists are very interested in now, about the same time. But Podolsky said physicists shouldn't wash their dirty linen in public. So he didn't like that at all, that it went to the newspapers. But anyway, what the idea was what they now called an EPR pair. You can put this pair can think of it as a pair of these particles, the two particles in the entangled pair inside the box, electrons maybe, and you somehow manage to switch the box walls off, and the electrons will repel each other and shoot off. They'll shoot off in opposite directions because they have to conserve the total momentum to be zero. So they'll move in opposite directions and fly away. And if they don't meet anything on their way, they'll stay in this entangled state. And so then you can start, the problem was, did the electrons decide that one would be up and the other be down at the moment they flew apart, which is what Einstein thought must happen, or would they stay in this entangled state? So Einstein thought that if an experiment could be done to test this, it would dispose of quantum mechanics. But other people, David Bohm, and then later famously John Bell, made a deeper analysis. And one of the issues are you can wait until you can decide which direction. You have to measure the projection of the spin on some axis. And each measure at either end could actually make a random choice, which only happens after the electrons have left each other and flown apart, and make decisions about which axis to choose. Okay, so there's underlying all this, there is a kind of problem with so-called free will in quantum mechanics. If you take quantum mechanics totally literally, you might believe that everything has been preordained and there's no such thing as free will, and perhaps it was ordained which direction the experimentalists would randomly choose to do their measurement in. Okay, that's still a kind of tiny philosophical kind of gap in the EPR experiment. But the analysis of Bell showed that you could find certain measurement outcomes were completely incompatible with the idea of local realism. And when these measurements were actually made, one of the first people to make them, I'm not sure if he's the original claimant on this, is Alain Aspect in France, but they confirmed Bell's experiments, and they came out with a violation of local realism, which was Einstein's preferred competitor to quantum mechanics. So, okay, quantum mechanics works. However, this entanglement over large distances is quite difficult to achieve because for example, the chemical bond is very strong when the electrons are close together, but there's a large energy gap kind of stabilizes it, right? You need high energy sunlight to break the bonds and cause you skin damage and things. So, but when the things are far apart, it becomes much more fragile and against what we call decoherence, interaction with the environment and loss of this coherence between the two electrons. So Aspect's experiment actually used photons, particles of light, rather than electrons, because light can travel very large distances without encountering anything that causes it to become decohered. And we see light coming from the Big Bang after all, or coming from the event when the atoms formed, and a little bit after the Big Bang, I guess. And of course, light has two states too. It's the two states are either the polarization of the photon, vertical or horizontal, which typical sunglasses are kind of screening out, or more interestingly, circular right-handed and left-handed polarizations. So using optical fibers, initially started off with experiments under Lake Geneva, but it's ended up, the Chinese claim to have made EPR pairs involving the ground and things on a satellite. So you've made large entanglement over large distances of photons has been achieved. Okay. So classical, one of the ingredients of the current revolution is a kind of mixture of quantum materials and quantum information theory. And the two kind of separate things which partially have come together. So classical information is stored in a bit, a switch which is either on or off, up or down. And that can be achieved by a little magnetic domain where the magnet is north, the north pole of the magnet is pointing upwards or pointing downwards. That's typically like an old style disk drive. While quantum information is stored in the state of a single spin. And the quantum spin, we can measure its spin along any direction. We can make it point in any direction. So the degrees of freedom of a quantum spin are essentially the same as a sphere. This is called the Bloch sphere. And the state of the system is represented by a complex number that you can associate with points on the sphere. So there's a lot more, obviously a lot more information in the direction, but you can't make a distinction between two different directions. The direction, if the direction is this way, it's predominantly in that direction. So if you measure its projection onto an axis, you'll either get it pointing that way or pointing that way. But the same state, if you point the axis in the direction of the spin, it'll be 100% pointing this way and 0% pointing the other way when you measure it. If you use an axis here, it'll be something like cosine theta by 2 squared in that direction and sine squared theta by 2 in the other direction. So you can prepare it in a given state, but if you measure it in a different axis, it's going to be some chance of it pointing one way and some chance of it pointing the other way. And another big difference between quantum information and classical information is classical information is unaffected by copying it, right? The people who want to, download songs off the internet, they kind of say, I'm not stealing anything because the original copy still exists. I just copied it, right? But and in fact, classical information is rather difficult to get rid of. If you want to recycle your cell phone, you've got to do some work to kind of get all your bank information off the hard disk inside the cell phone and erase it. So you have to do work to erase classical information. But so quantum information is much richer. It's also more fragile and it's got some limitations. Okay. And two of the important statements here are that the quantum information or the direction, the state of the qubit, as we say, it cannot be cloned into multiple copies. On the other hand, you can do interesting things like in Star Trek or whatever, which I believe has a local hero involved. Captain Kirk is a Montreal guy, right? So that you can actually so-called teleport the information, right? So no cloning property tells us that we can't, as I say, like I've got a qubit here and I've got another kind of empty qubit that I want to put into the same state as this one, and I can't do it. What I can do is I could take a qubit and a blank slate, and I can end up with the blank slate containing the information, but then I don't have the original information got destroyed in the process. And so that's the famous teleportation. And teleportation is actually why we talk about entanglement as a quantum resource for computing. So if we have our target qubit that we want to kind of copy or transport over here, we actually have to start with a remote pair that's entangled. A locally entangled pair is pretty boring to some extent, but what's extraordinary in these things is if you can manage to extend this pair over a long distance, keeping the entanglement. So this is like the EPR pair, right? So you have to stretch this locally entangled pair. So you've got an entanglement between one point and an entanglement between a point which is some distance away. And now the teleportation measurement system works by, I can take this system and I can make a joint measurement of the system of this end of the entangled pair and the test qubit. And I can make a measurement that has 4 possible outcomes, it turns out. And this is, of course, where you don't violate relativity, because you actually need what's called a classical communication channel. You have to pick up a telephone and talk to somebody at the other end of the line and tell them what result your measurement showed. And then based on which result you found, they can do an operation on the qubit, which will exactly reproduce the original qubit state. And in the meantime, what's left behind after all this is you have some kind of locally entangled pair, but it's got no useful information in it. So the teleportation required you to actually send information classically, which required not less than the speed of light, slower than the speed of light to actually communicate it, but you managed to transmit the information. Okay, so this is what leads to the idea that this kind of entanglement, in particular entanglement over distances, whoops, sorry, let me get rid of that. Yeah, so remote entanglement is the key thing. So how do we produce entanglement? So any two systems will become weakly entangled if you bring them into contact, right? Once they interact with each other, a little bit of entanglement happens. We want to get this kind of maximal entanglement, this kind of bell pair where you have up, down, or down, up, which is the strongest kind of entanglement you can have, not weak entanglement. So in the chemical bond, the Pauli principle kind of does it for you, right? You can't put them in the same place unless they have that entangled property, but it doesn't, of course, work for remote objects. So to make 100% entangled bell pair, you have to start with 2 qubits in a known reference state. You have to bring them together and connect them under what's now called a gate. And you have to switch this gate on, and then at a very precise time, switch the gate off, where they're exactly 100% entangled. Because if you do it too early, they will be not quite entangled. And if they do it too late, they'll have gone past the thing. So it's quite a delicate procedure to actually get 100% entanglement. We'll see that. Okay, so what about topology? So as I say, around 1980, 2 things which didn't seem connected at all at the time came up, which both turned out to be original examples of topological states of matter. One was the quantum spin chains that William talked about, and the other is the quantum Hall effect, which Klaus von Klissing discovered experimentally around the same time. So in the meantime, these 2 unconnected things have become part of a large kind of continent of different kinds of topological effects. And we now really know that there are different kind of condensed matter where essentially entanglement properties play a key role. And as I said, before this time, no one, at least in condensed matter, really thought about entanglement as a property. So topological matter differs from ordinary matter because it's got some properties, which really probably are entanglement properties, that can be described by whole numbers. 1, 2, 3, -1, etc. So ordinary matter might be described by a boring number like 0 or 1. I mean, 0 is clearly not a boring number, but it took a long time to discover in the human history. But anyway, so the basic thing is that states classified by different whole numbers can't smoothly change into each other. So if you have a region where the state of matter is classified as -2, and embedded in a region where it's classified as 0, something interesting has to be happening on the boundary because you can't smoothly go between 0 and 2. And that's the basic key. The topological properties of materials can't change continuously, which makes their properties robust against small amounts of disorder like dirt in the material. In our current technologies, silicon clean rooms where you make these ultra clean wafers, the workers are dressed in these kind of elaborate protective spacesuits. They're not to protect the workers from the noxious chemicals involved in the manufacture. They're to protect the silicon chips from bits of spit and hair coming off the workers. Little bit of dust on one of these silicon wafers ruins it. So it has to be done in this ultra clean room. So the forgiving nature in principle of topological things is actually a good feature. So the classical example in mathematics of topology, of course, is the classification of closed surfaces by their genus or the number of holes in the surface. And a shape like a sphere with 0 holes can easily be distorted by small forces, from a soccer ball to American football or whatever. But only a violent event like poking a hole through the middle can change it into a donut. And of course, there's no such thing as 0.3 of a hole. You've got a hole or you don't have a hole. So the geometric properties, such as curvature of a surface, they're local properties, but integrals over local geometric properties may characterize global topology. And of course, Gauss was an incredibly productive mathematician, but the discovery that he made that he thought was the most amazing and extraordinary discovery he made was, he called this as theorem egregium, was that, well, the surface area of a sphere is 4 pi r squared. The Gaussian curvature is the product of two radii of curvature, which is, or inverse radii of curvature, which are both 1 over r on the sphere. So he discovered that 4 pi r squared times 1 over r squared is equal to 4 pi. But of course, what was amazing about that was that if I squashed the sphere from a nice round sphere into the American football or a banana or whatever, it still stayed equal to 4 pi. And so this is true for any compact 2D manifold without any holes in it. And of course, nowadays, theorems, people giving talks, experimentalists in particular, love to show movies of coffee cups turning into donuts when they give talks about topological insulators. And of course, the Gauss-Bonnet theorem basically says you've got the torus. Now, the bagel has regions of positive curvature on the outside and negative curvature on the inside part, and they exactly balance out. So you do this integral, you get 0. So it's actually 4 pi times 1 minus the genus. You do it for what was called in Stockholm the Swedish pretzel, which actually doesn't really exist because the 2 holes in the thing actually get filled in when you bake it. But that's topologically equivalent to what's called a loving cup, while the bagel is equivalent to the coffee cup. Well, of course, the true pretzel actually has 3 holes in it. So it gets minus pi when you integrate on the surface. And that's, well, there's also a cup that goes with that, as you can see. No one actually knows exactly what this cup should be called. I've heard it suggested it's called a California loving cup, but I'll leave that aside. So anyway, in 1944, the mathematician, a Chinese-American mathematician, I guess he was American at that time, he became Chinese-American, became Chinese again afterwards. Chern, he generalized Gauss-Bonnet theorem to a much more abstract theorem about abstract curvatures on abstract manifolds as opposed to real surfaces. And this is actually the form that applies to the quantum problem quite often. And in fact, there's a medal, since there's some story that Nobel was prejudiced against mathematicians because of some issue with his wife and then a mathematician. So they didn't give mathematicians didn't get a Nobel Prize. And then there was this prize, the Fields Medal, that only young people, you know, tremendous amount of ageism because you can't get it if you're over 40. They invented a couple of prizes, the Abel Prize, but now there's also the Chern Medal, which is worth $500,000, I guess, 50% for the recipient and 50% for his research. And that's got the Gauss-Bonnet Chern formula on the back of the medal. And I guess it was just awarded, it's awarded every 4 years, and this year it went to Barry Mazur at Harvard. Okay, so there's a Nobel Prize makeup term for mathematicians. And it has the Gauss-Bonnet Chern formula on the back. So in recent years, it's been realized that quantum condensed matter can exhibit these unexpected properties, which turn out to be possibly related to kind of long-range quantum entanglement. So what do I mean in this? If I take a trivially entangled system, it's basically the quantum state of the whole system is basically a kind of almost a direct product up to weak terms between the right side of the system and the left side of the system. So I can basically think of the unentangled system as really, you know, just build up of just building 2 bits together with nothing special happening at the boundary. The quantum systems which are entangled, they have some kind of edge state around them typically. And they kind of, if I try to cut them in half to separate them, this I could easily separate, they kind of resist for a while, but if I pull them strongly enough to separate them, eventually they do separate, but now the boundary, the edge states which existed around the whole thing now extend to the place where the cut was. So it's a bit like trying to, you know, pull a magnet, trying to separate, it's a separate thing, but trying to separate the north and south pole of a magnet. You chop it in half, you don't manage to get an isolated north pole. So anyway, this is a kind of, well, if I take topologically trivial states of matter, I can sort of arrange them just by bringing the atoms and putting them next door together, a bit like, you know, these two things are not entangled. I really just stack two boxes next to each other. So trivial matter is sort of, can be modeled by this picture of just assembling atoms. And if the matter is non-trivially different from just assembling atoms, then something has to happen along the route when I bring them together. Something has to change topologically. I cross a boundary to a different topological state. And the electron boxes or orbitals that used to be centered on the atoms get rearranged to be in different places and connect them. Okay. So in heavier atoms, the electrons in a group of atomic orbitals, these little boxes, get locked together. It's actually because the Pauli principle keeps parallel spin electrons apart from each other, they lower their repulsive Coulomb energy by going into this set of boxes, a d orbital or what, all parallel. So you can build up magnetism in these atomic boxes, and the spins want to add up all in a line in parallel. And we've classified the elementary spin as spin a half. So if I have so the total spin will be a whole number times a half if they're all kind of lined up. And so if the whole number is even, it's integer spin, and if the whole number is odd, it's half integer spin. So around 1981, I discovered this, that a chain of spin 1 atoms could have a kind of novel magnetic state that's now understood as the simplest of the topological states. So in this thing, the original expected state, the spins, these are spin 1, so it's actually 2 spins in parallel. And they want to kind of line up, actually they lower their energy for various reasons by being both up, both down, both up, both down. But this is a previously expected state of this material. And you can see it's basically the same thing you get just by taking these atoms, arranging their spins to point either up or down and just pushing them next door to each other. Okay, it's just a kind of simple assembly. It turned out that what this system actually wanted to do for quantum mechanical reasons was something like this. It wanted to split the spin 1, and half of it would join up with the neighbor to form an entangled singlet, and half would join up with the other neighbor. So you ended up with the spins forming this kind of entangled thing. So if I tried to cut it down the middle, I would have to cut one of these entanglement bonds. And then you're left over with half of the spin at one end and half at the other end. This is turns out to be now very typical of a topological state of matter. Something at the boundary is different, right? There's half of a spin left over at this boundary and half of a spin left over at the other boundary. So actually this result that I found turned out to be, it was an inescapable consequence of a new way I developed to look at this system based on my thesis work. But it was completely contrary to the ideas of the magnetism community at the time. And it shocked me because it said that the conventional wisdom had to be 100% wrong about this. The conventional wisdom said there was no difference between integer and half integer spin. Just the system, the quantum fluctuations just became stronger the smaller the spin was, but it was some kind of continuous process that didn't matter, didn't depend on the spin, twice the spin being a whole number, right? And it shocked me because it contradicted what quantum magnetism people expected. But what they expected actually was quite wrong, but it was really only wrong because no one had even dreamt about entanglement at that time or thought about entangled phases. And in fact, these ideas were kind of denounced as nonsense by senior people. And somebody stood up at a conference where I gave a talk, a big shot guy stood up and said, "This is complete nonsense." But you know, science is great because you can have your opinion about stuff, but in the end, experiment can be done, right? And so it's not a question about angels on a head of a pin or anything like that. So science, modern science now allows you to check things, and nothing like a controversy people love a controversy, right? I mean, for experimentalists, the best thing they can do is prove a theorist wrong. Well, the second best thing they can do is prove somebody right? But in either way, people start thinking about ways to test things, right? And in fact, one of the key things in the modern developments is the use of material science, the developments in material science who can turn toy models which exhibit interesting effects into reality by working out how to actually build them. So people got together and built a chain of atoms, nickel atoms, which are spin 1 in some organic chain. So they realized this thing, and in the end, the experiments showed that the predictions were correct. And in fact, the theorists, a number of important theoretical ideas, in fact, involving entanglement, density matrix renormalization group methods, were actually created in part to test these ideas, right? We're going to find out, are they right or are they wrong? We're going to find out all kinds of new ways to do it. So it actually led to a lot of developments, and controversy is actually a great thing for science because it leads to a struggle between ideas, kind of leads to all kinds of new innovations. So anyway, so the meme in this thing is that if you have a line of people, you expect people to come unless they've been kind of injured or something, mutilated, everyone has 2 hands, right? And but this principle that it should be 2 hands could be valid if you form a chain where people link hands up together. You've created this entity where there's one free arm to wave around on one end and one free arm to wave around at the other end, and that's how you've managed to separate these apparently pairing of the hands. So this actual principle will come up again in a bit. So the new state turned out to be the simplest possible example of this kind of topological states of matter. And that, although the simple model for this was not my original model, it ended up on my Nobel diploma. It's called the AKLT model, Affleck, Kennedy, Tasaki, Lieb model, which showed up the principle I came up with in a very clean and crisp way. So the quantum Hall fluids actually are perhaps the clearest example of topological states rather than these. And they originally were found in very high magnetic fields. And in high magnetic fields, electrons want to kind of move in circular orbits around the direction of the magnetic flux. And if the electrons are confined to a 2-dimensional surface, they're stuck in that surface and they go around in little circles called Landau levels. And what von Klissing discovered, he did a measurement of what's called the Hall conductance. You measure if there's a current flowing this way in a magnetic field, it actually induces a voltage drop across the surface, because if the electrons are circulating in that direction, they'll end up on that surface. If they're going in the other direction, they'll end up on the left surface. And that allows you to tell the things that are usually moving in a wire are electrons. The old, under Franklin and people working out, you actually didn't have a method to determine whether the charge that was flowing was positive charge flowing one way or negative charge flowing the other way. But Hall's discovery was that you could use magnetic fields to tell what kind of charge was flowing. And so what von Klissing discovered was this Hall conductance, which is measured in inverse ohms, was an integer times e squared over h, 2 fundamental constants of nature. And of course, this is a great surprise because you expect not to get whole numbers out of some measurement. And of course, from a modern perspective, it took time to understand that means that this has to be topological, that the integer involved. And this has actually led to I guess, decolonialization is a very popular term, at least in Britain these days. I know about Canada, but it's decolonized the kilogram, which was kept in the imperial vault set up by Napoleon in Paris. So if you actually wanted, if you wanted to check your market that you got a kilogram of potatoes, you had to, in principle, go to Paris and knock on the door and beg to check against the official kilogram, which was a lump of platinum, which is now consigned to a museum because you can now use the quantum Hall effect and the Josephson effect to build something called a Kibble balance that everyone can have their universal quantum device, which will give you an exact way to check per kilogram. So it's actually a huge change. It's not based on a lump of metal. So the topological nature of this took some time to understand, but if the electrons are going around one way inside this thing, you can see that if they actually get near the edge of it and start to hit the edge, they'll kind of bounce off and they'll go around the edge in one direction, which is the opposite sense to which they're rotating, okay? And that turns out to be a typical example of an edge state. These quantum Hall states have edge states that actually act like one-way streets. They go one way. If you reverse the direction of the magnetic field, they will go the other way, okay? And also, because of this, there's some kind of thing called the Fermi level, but the Fermi level is pinned at the edge of the sample. In the Landau levels, things that go around in orbits, so there's a kind of natural energy level, which is Planck's constant times the angular frequency of the orbit, which leads to a gap. But the stuff at the edge ensures that the chemical potential or the Fermi level is pinned somewhere in the gap, and you don't have to use any kind of fine tuning to produce this effect. In fact, the effect was seen because von Klitzing turned on what did he do? He put a constant current through his device and then turned on the magnetic field. And it didn't require the magnetic field to reach any precise value. It just had to make sure that the chemical potential was in the gap. And he found the same, he used a digital meter, and the same number came out to about, at that time, about five decimal places. And they thought there had to be something wrong with the meter, with the digital device, because every time it was reading exactly the same number up to some precision. While someone else had done this experiment before where they put the thing in the magnetic field and then ramped up the current, and you never get to the same value of the current, so you never get to the same Hall voltage at the thing. So how you do the experiment, having the luck to do the experiment the right way was what, you know, exposed von Klitzing to the fact that the number didn't change. Okay, so the integer Hall effect was followed by all kinds of bigger puzzles and more Nobel Prizes floating around. The fractional Hall effect was one of the things we're talking about in this workshop. And Laughlin discovered it, and these guys got the prize. The guy actually built the device, got left out because you can only have 3 people on the Nobel Prize. They did the measurements, but you can see this is actually the device the thing was seen on. And I mean, you wouldn't get a job at Intel if you produced that as a kind of example of your soldering abilities, right? But so it shows the forgiving nature of topological states. And the key thing was that the Hall effect, the fractional Hall effect, which is just, people just managed to explain the integer Hall effect. It had always had to be an integer. Now they found it's a fractional, but it's actually because essentially you've got fractional charges floating around in this thing. So it's an integer number of fractional charges. So anyway, it's still topological. And there's a lot of interesting stuff, in particular in that case, when you have stuff going around the edge one way, and you have little objects, little vortices that if you move them around each other and exchange them, you get not +1 or -1 like for fermions and bosons, but different phases. And that's taken some time to verify, but the recent experiments have actually proved this so-called braiding in this abelian quantum Hall effect. But the most interesting thing is, which is people are hoping to use for quantum information, is so-called non-abelian quantum Hall states. And these are states where you can where there's actually hidden information inside. You can hide information inside the system and process it in a way that's protected from interacting with the local environment. So that's an attempt to, that's a on paper proposal to avoid the issue of loss of quantum information by so-called decoherence, and do it in a possibly scalable way. Okay, so there are a number of current attempts to build quantum devices, but no one's come up with the thing that you can actually scale from you know, a few tens of qubits to a million qubits, right? And then in the regular one, you've got this problem with the gates. You've got to do all this very fine tuning to switch things on and off at exactly the right time. So there's a lot of, so this is actually, on paper at least, is a great possible thing. So the non-abelian states can hide information, and you've got these little vortices inside them, and you braid them around, and the information, hidden information, is stored in the configuration and is kind of mixed up, and the state of the qubits are kind of changed by moving these things around each other. And provided they don't get close to each other, the information is the braids, the thing is protected. And so the people who discovered this state initially were Moore and Reed, but the person who popularized this as a possibility for quantum computing is Alex Kitaev, who's at Caltech these days. And so basically in this structure, that if you put n vortices in it, it creates n minus 1 by 2 qubits. Okay. So where's this structure? So the simplest qubit you can make out of this thing involves 4 vortices. So this is a thing, it's got the edge state going around one way at the edge, and the vortices are like little empty boundaries inside it where there's a kind of edge going around in the opposite direction. And it turns out that these vortices are like, in some sense, half vortices. You can't create one of these things locally by itself, but you can create a double vortex at some point by removing an electron or adding something to the system. So they can't be, these are kind of objects that can't exist on their own, but they can exist when they're brought together, and that's how you create them. So to create the 4 vortices, you had to create 2 of the double vortices and pull them apart. And pulling them apart leaves this chain of entanglement between them. Now you can make exactly the same pattern of 4 vortices by creating them here and pulling them apart, and it would leave a different entanglement chain. And this pattern here would correspond to the qubit, the Bloch sphere pointing up. And this pattern, in fact, corresponds to the Bloch sphere arrow pointing to the left. And by bringing these guys and moving them around each other, by braiding them, you kind of stir up this entanglement pattern to a new pattern. And each different entanglement pattern corresponds to a different direction of pointing on the Bloch sphere. So by screwing around with these things, you kind of move, you've got the control of moving the quantum state around. And the information is nowhere locally stored in this device. It's stored kind of everywhere in the region containing the 4 things. So if I take a gun and I shoot a hole in it through here, I've got an exponentially small chance of killing the information, right? Because the information is spread out locally. I guess the hole might manage to kill the information, but I've got a very small chance of it, and it gets exponentially smaller as the further apart I make these objects. So a state with this signature, this so-called non-abelian quantum Hall, has been experimentally seen, but it's proved difficult to work with because it requires very high magnetic fields and ultra low temperatures. And it was later realized that this basic principle, the separation of what are now called Majorana zero modes, can be achieved in other systems. And in fact, Microsoft have put a lot of money into this topological quantum game. I mean, Google have gone with one different kind of thing called adiabatic quantum computing, and IBM have got little superconducting qubits. And then there's ions on a chip. There's lots of different attempts to make qubits and assemble them into devices. So the braiding, the braiding of these things which are called Majorana zero modes, which I'll come to in a second, is actually the central idea of Microsoft's approach to this thing. And well, you know, initially 2017 was had been, predicted, oh, this is going to go fine, we'll make it. They expected to produce braiding in 2017, but 2017 came and went, right? And but apparently maybe it's just propaganda, I don't know, some inside information or something. Anyway, things look discouraging, but the word has been that apparently the things are actually going better than expected, and they don't want to publicize it too much because of trade secrets, but who knows. But anyway, it seems to have some encouraging results that maybe this stuff is actually getting somewhere finally. So what is it? In 1937, just before he mysteriously vanished, some people think he went to Argentina, but other people say he threw himself off the boat. He went on a boat trip. Majorana was a kind of slightly weird student. He was brilliant but weird, like many physicists, I guess, and mathematicians too, I suppose. Yeah, he came up with this idea of Majorana decomposition of Dirac equation, and in fact, he didn't actually get around to writing anything up. So I think Pauli had to write it up for him. Fermi wrote it up for him, I think. Yeah, but anyway, he came up with the idea of now called Majorana fermions, which are kind of fermions which are there an antiparticle. And then he disappeared, right? And while the people hoped to use possible use of Majorana fermions in the theory of the neutrinos, it's not so clear that's actually going to happen. But it's actually become a fruitful thing originally in superconductivity, and more recently in topological quantum matter, as we'll see. And the weird thing there is, I mean, we just talked about there was a box, the orbital was a box you could put empty or filled, right? If I have some kind of something like a magnetic field or so-called spin-orbit coupling that actually prefers to keep the electrons pointing up rather than down, then I've got a box which is either empty or got a box which has got one electron pointing up in it and doesn't particularly like to have the second electron added to it, right? And the weird thing here is that if I actually put this object in contact with a superconductor, I can actually get the box, I can pull the box apart into two half boxes. The two half boxes can either contain one electron or no electrons, and they're the precise thing of the little half vortices I drew with the entanglement structure. The half vortices contain a Majorana zero mode at their center, but they can't be created by themselves. They're actually something that's been ripped in two. So that's so the remarkable feature there is so these are not called Majorana particles, they're called Majorana zero modes because they're actually half of a box that you can put an electron into. And this is actually at the heart of the Microsoft approach to this. And basically, as I say, that's it. You take the box, it can either contain the electron or it can either be filled or empty, and I pull it apart into two half boxes, and I can't tell them. I can't look by looking at these. I can't tell whether I pulled apart a full box or an empty box. It's because somehow the extra fermion, the extra electron, is somewhere spread out in this intervening space, and I can't see it. If I actually look at the boxes when they're reassembled, I can look at it. I can tell quite clearly by looking at the box whether it's full or empty, right? But once I've pulled it into these two half boxes, I've lost the information. I've hidden the information about whether it was filled or empty. So I've made the state of the qubit kind of impervious to decoherence, right? And again, if you can move these objects around, it's exactly this braiding principle. And also, the kind of way you can make gates and the thing, you don't need any of this delicate stuff about switching on things for exactly the right time to create the maximum entanglement and switching it off. So actually, there's a lot of advantages to this topological structure in nothing delicate is needed because it's topological, right? So this actually is a kind of beautiful dream of a topological protected qubit. And it's kind of, on paper at least, it's an intellectually satisfying answer to the problem of dealing with decoherence and robust scalability. But of course, practical people, technologists and investors and entrepreneurs need to have some skepticism about, the beautiful dreams that that scientists have. And of course, fusion power has been a beautiful dream, although perhaps it's actually coming. There's some encouraging news about fusion these days. So maybe it's one of these things that will take a long time to happen. But I actually personally believe it's a realistic dream, and possibly, it's being achieved. And I want to now just finally just relate it to the original thing I talked about. So in the this is a Kitaev model for a so-called P-wave or topological superconductor. And I bring this chain of atoms, which likes only to have, because there's something called spin-orbit coupling, it likes to have all its atoms, it likes to have the spins pointing one way, so it's got rid of the second spin. And it's brought into contact with a superconductor, and it's done somehow. This is the picture. So little wire put on top of a superconductor. And the interesting thing is that the superconductor kind of removes the electric charge from the electron. It turns it from basically the screening property, the electric charge moves to the surface of the superconductor. Actually, every electron gets a little oppositely charged image pattern in the superconductor above it. So it actually behaves like a neutral object, but still has this fermion statistics. So what the effect of that is that in the presence of the superconductor, the electron orbital, which I've shown here, can somehow split into two half orbitals. Okay. Now, originally, the two half orbitals are on the same site. So that's nothing special. That's just a mathematical rewriting of the formulation with no physical content. But what you're doing here is you're taking the fermion creation operator, which is actually something like a complex number, and writing it in terms of a real and imaginary part, which are both real numbers, right? So Majorana fermions are real, and regular fermions have a complex phase associated with them. And the magic of this thing is that you make this thing so they split up, but then you let them recombine, let the green and the red part of one of the orbital on one atom on one site can recombine with the red on one, the purple on one, and the green on the other. And that actually allows you to leave half an orbital on one end of the chain and another half of the orbital on the other end of the chain. And you've actually, by this magic, created these two half of a box, which are spatially separated from each other, which is the key thing. It's actually no point in having these things on top of each other, because that's just formal. But if you can actually make them spatially separated, then you've got something you can play with. And so actually, that's exactly the same principle as was shown up in splitting the spins into the half, except now it's a much more exotic thing I've got left over at the end of this chain, the Majorana zero mode. And then there's some issue about how I can turn this into a two-dimensional system where I can properly have four of them and braid them around each other. That's just one of the quests, the Microsoft version of the quest for the holy grail of quantum computing. As I say, there are lots of other approaches. There's nitrogen vacancies in diamond, have a nice qubit in them, and ion trap qubits, which are looking very good these days. Transmons are little superconducting rings. There are lots of different proposals, and people are getting them better and better. But we still have this issue about, to actually build a real device that's useful, you actually need to have some kind of error protection against errors, and you need scalability, right? And who knows what's going to happen? I don't really know what's will finally emerge, but there's so many people working on this quantum information and quantum materials from different viewpoints, and we're certainly learning new things, and I feel confident that something's bound to come out of this thing in terms of usable technologies. So finally, the moral of all this is actually, my role has been as a kind of toy model builder in finding very simplified models in which exhibit some of these effects. And there's also needed deep mathematical understanding to understand the topology and Chern classes and these various things to explain really what's going on. And then the key thing is also the material scientists who actually managed to build the thing. So it's actually a cooperative work which brings different classes of people together who maybe wouldn't talk to each other so much, but now they have to talk to each other to get a common purpose fulfilled. And anyway, so out of all this stuff, I'd like to actually leave with a motivational message for. So actually, some of these discoveries, like what I found and what von Klitzing found and things, were like totally unexpected, right? And they were not motivated by looking for what we found. So the message is actually to find something that's really surprising. It's not a question of being a really smart person, right? If actually there are plenty of smart people around, and if people have an idea there's something out there to be discovered, the smart people will have got there first, right? So the key thing, but the most amazing discoveries are the unexpected things that no one was expecting, including yourself, right? So you don't actually have any competition for those because no one's out there looking for it. Of course, you actually have to be somehow your path in science has to take you on a walk that happens to take you past in the neighborhood of one of these things, right? And of course, you can be walking around the path and kicking the dust as you go along. But if you don't look down at your feet and notice that you've kicked up a huge diamond, you'll just walk on by and leave it. And maybe if someone else walks down that path later, they'll probably find it. But the key thing is you actually have to, if something unusual shows up, you need to somehow be able to take a little bit of time to try to understand it. Most of the time, the unusual thing will be vaguely interesting, right? But very occasionally, it'll turn out to be something like the diamond that no one imagined was there. And so I think anyone who starts off in a career in science, provided they've got the ability to step aside and look what's happening rather than be totally focused on a given end result, has got the opportunity. Obviously, it's very small because luck is involved, right? The luck that takes you past the thing that was there waiting to be found. Of course, you also need the preparation to realize that there's something interesting there. So you do need a preparation, and usually you need the commitment to actually follow through. If you really think it's interesting, you probably have to kind of fight for it, as I found, because anything that's against the status quo, obviously, usually things which are against the status quo are wrong, right? There are plenty of, I get Einstein was wrong emails all the time, right? But, anyway, things need to fight. So this is actually probably the same kind of thing that people give in a business school commencement talk. You need to you have to seize the opportunities that when they present themselves, and you need passion to really push something through and that. But anyway, there you go. That's the story I was telling you. And okay, this one is just that scientists do have a job to try to explain to the politicians and the fundraising and the public about what's going on. And there you go. Thank you.
All right, well, thank you for a very entertaining talk. So it's now open to questions. I also encourage students to feel free, or anyone who wants to be the first. En français aussi.
I won't give you any, je donne pas investment advice. Pas placer votre fonds.
Oh. Okay, maybe Dennis and then Fiona.
So thank you very much for your excellent talk. Just one small remark. I think as experimentalists, I think the biggest satisfaction is to actually do an experiment that theorist has never thought about. But anyway, on this serious point,
well, von Klitzing did that.
Yeah. So about 6 years ago, I heard a talk by Anton Zeilinger.
Mm-hmm.
And he made a remarkable point, which I agree very much with. And he said that progress in physics, in particular, has been kind of driven by asking a very simple question about a physical principle.
Yeah.
And he gave an example that the moment you try to understand what it means to be simultaneous with event, then obvious things fall out, as we know. And he made a point that the key question in quantum is entanglement, as we said. But he says, I still don't know what question to ask about entanglement.
Yeah.
So it's a very broad question, but I don't know. And you obviously have thought much depth of this.
Yeah, people haven't. Yeah, a full understanding of how you classify entanglement is still kind of missing, right? They're kind of, for two objects entangled are mathematically very straightforward, but three objects, there's been tackled, like Zeilinger, for example, tackled the three object case. And but yeah, it's to actually quantify entanglement of more than one object, and when it's spread out, is again still a challenging thing. And this notion of the entanglement as the fuel is semi-quantitative, but not totally quantitative, right? And no, there's a lot to learn, but the basic point is I never heard about entanglement till as apart from some kind, philosophical issue about free will, right? And quantum mechanics that philosophers worry about, until probably realized in the early 90s that the so-called density matrix for normalization group, which was actually created to test the spin chain problem, was actually essentially using entanglement methods, not calling them entanglement. So yeah, so we don't really understand it, and it's as I say, it used to be that the Heisenberg uncertainty principle was the thing people gave a public talk about quantum mechanics, but really, it's Einstein's insights really that even though he thought it was so crazy it had to be wrong, really has focused the thing. And it's entanglement is certainly, in my view, the central property of quantum mechanics, where it used to be a peripheral kind of minor issue or something. And who knows where things are going to come from this, but we're learning a lot in this. We're learning a lot about how to manipulate quantum systems and exactly where the information is and how it spreads and stuff these days.
I think my question was maybe a slightly more specific version of the same thing, but when you take these systems of same IRRs, like what's the is there a preferred entanglement measure? It's a kind of it should be channels within or
okay, I can actually.
Maybe that's
Oh, I don't have it on this computer. Yeah, but if you actually do a calculation, put some of these things, put four qubits like this on the surface of a sphere, right? 4 Majoranas on the surface of a sphere, and put them in different states, you actually see when because they're close together, there's a kind of, they look the same in broad, but there's lots of little interference fringe patterns. And as I rotate the qubit that they form, the spin direction on the Bloch sphere, the little patterns change. Now the patterns fall off exponentially with distance from these things. So as I make these qubits separate, there's a natural length scale here. As I bring them from far apart on this length scale, the ripples get exponentially small, so they become invisible. But you can see that when you bring them close enough together, you can actually see what the state of the qubit is, but it'd be very difficult. The measurement gets worse and worse because the interference ripples become much lower amplitude as they fall off with distance exponentially. So the information, the topological thing views these objects as a point, right? With no kind of length scale. All these things actually have a length scale. When you, for example, when you have the things going around the edge of the quantum Hall thing, the edges have to be separated by a large enough distance, and then they become completely independent. So the topological idealized form ignores the fact there's a natural distance involved, but because things fall off exponentially with the distance scale, the chance of being able to make the measurement falls off exponentially too. And so that's why things are effectively hidden, provided the distance between the objects that you're braiding is large compared to that microscopic distance length. Yeah, but yes, you can look at this thing and you can see the little pattern kind of changing as I rotate the thing on the Bloch sphere.
So, question. My colleagues probably sometimes ask stupid or of silly questions.
That's what Wigner used to do.
Stick my neck out once again. I was mightily confused by the few slides discussing the creation and destroying of qubits. And that's, it seems to imply that it must be impossible to create a qubit in a predetermined state.
No.
Otherwise, you can measure for a qubit if you manage to fully measure the entanglement state, measure the direction of the spin axis of the quantum numbers. So you can create another system with the same state. If you cannot do that, you cannot ever create such a system in a predetermined state.
Well, you
can never use a quantum computer to transmit information that you want to transmit, rather than information that happens to be randomly in a qubit.
Well, I mean, with a strong enough magnetic field or whatever, you can make the spin point upwards, or you can guarantee that the box is filled. The issue is whether you can, if you're given a qubit in an unknown state. The problem is, once you know what the state is, the information that's stored is lost, right? Because you did looking at it, you did some kind of measurement. You had some arbitrary choice of axis was made, but you did a measurement and you put it into a known state. So that meant you threw away all the information that was in it. The issue that you can't, the no cloning theorem says if I'm given a qubit in a unknown state, if I want to do error correction, right, I might say, well, I just want to make lots of copies of my qubit and do the calculation and, you know, find out which one is not the same as the others or whatever, or repeat it enough times that way. You can't make a copy of an unknown state which contains information. You can't clone it. So that's the basic principle that says you can't, that makes it much more difficult to do error correction on things. So what you can do is you can tell whether you can take a group of qubits, you prepare them in the same initial state and then do the same things to them as part of your program, right? You're not allowed to measure them, but you can do something that tells you that one is different from all the others, right? So you can somehow find out that one is not the same as the rest of them. And then that one, you'll decide that one went bad, something happened to that one, I throw that away. And you just hope you get to the end of the calculation and still have some duplicates left, right? So you're not allowed to measure what they are, but you can do a measurement that says tells that you can compare them and say, are they in the same state or not, without actually finding out what state they're in. And that's the current thing. But the thing that means you need more and more actual qubits at the beginning of your calculation to hope to have any left over at the end of the calculation that didn't have to get thrown away along the end. So that's what they currently call NISQ, noisy intermediate scale quantum computing, which is being done with like ions on a chip and things, but it's not really scalable. This is when Google talks about quantum supremacy and things like that. They're making a NISQ device, and basically with a NISQ device, if two of the qubits are, if you do the measurement at the end of the thing and two of the things are the same, if you get the same result for two copies of the runs of the thing, you say, well, that one has to be correct, right? But that relies on, but in the general case, if you run for long enough, they'll all be in different states. So you won't have two which survive the calculation to be in the same state when you measured everything. So you're fighting against the exponential, decay times, and that's the dream of the topological computer, that the stuff is actually non-locally hidden. It's still danger. Actually, the danger part is you have to bring the objects together to put the information in. So there's some risk when you pull them apart. During the time they're close together, they're liable to go decoherent. But when they're apart, on paper at least, you can do as many of these braiding operations. You can run the program for as long as you want. sort of on paper at least. The danger parts are only the initial feeding the information in and extracting it. To get it out at the end, you have to bring these things back together and find out whether the little box is full or empty thing. So it's an advantage anyway. On paper, it says the computer program can run a lot longer. You still have this worry about the data in and data out parts of the thing. But
Well, the last question in the back.
Given the general nature of the talk, I have a general question to ask. So now that topological mathematics are becoming mature as a field of research, always mature. So in your opinion, what do you think are and there are unifying themes that are emerging between these many systems that you spoke of? So what do you think are the major open problems, or what do you think the community should focus its efforts on? Sort of like an analog of those 23 problems.
Yeah, well, as I said at the end, there's really three groups of people have to get together. And right now, probably the key thing is actually the experimental end of things, to actually demonstrate a qubit. And it's probably, I mean, it's not clear. I mean, there ought to be a Nobel Prize at the end for someone who manages to demonstrate the braiding and basically put some information in, do some of this braiding, and read some information out that's consistent. Now, of course, there's theorists and there's experimentalists. There's various people who have claims on all this stuff. There might be too many people for a prize, but that's the step people are waiting for. The step that was overconfidently predicted going to happen in 2017, hopefully will happen at some point. But yeah, so there's a lot of work, for example, on designing the equivalent of C or Fortran or COBOL or whatever for language for programming quantum computers, but very much based on Pauli matrix algebras. But it's not clear until we actually have the kind of devices what the real how the algorithms should work and things like that. But I don't know. There's lots. The sticking point, but as I say, there is progress certainly in noisy intermediate scale computing, and you know, I mean, whether or not, I mean, you can go online with IBM and do stuff on their quantum computer. I guess you can book some time. School kids could do it apparently. When I was at school, there was a program where with a hand punch, you could punch some Fortran code on a little card, and they got mailed somewhere, and a week later you got some result back. That's probably a bit like that for quantum computing these days, early days, but yeah, you can actually play with quantum computers. IBM at least as a publicity stunt or something, kind of allowing you to, I mean, online you could play with the quantum computer.
Okay, so I think I'll thank Duncan again for his lecture.